Good. Sorry. Sorry. Come on, where's the projector now? Oh, there we go. Okay. I'll do that question again. Which one page was it now? Page 87. I realised I said something wrong yesterday when I was on the bus going home. I'm like, hey, that's not true. So I'll tell you what I said wrong. And maybe someone can tell me. I said wrongly that the speed of the water at the bottom is the same as the speed of the water at the top. Yes, well, I said wrongly. So, no. First question is, why is that not true? Yes?
Because water is influenced by the pressure.
There's a pressure factor, yes, but so simplify it a bit more.
The more higher, the lesser the height of water, the lesser the pressure.
No, I'm complicating it. Keep it simple.
The particles above the water?
No. So what's happening is the reason I said the velocities need to be the same is so that the water doesn't build up. And I was trying to think of like Coulomb's conservation of charge. Remember with Kirchhoff? 1 Coulomb in, 1 Coulomb out. It was wrong of me to say velocity is the same. I should have said the change in mass is the same, not the change in position. Are you listening? What did I just say? That's right. Listen. I should have said the change in mass is the same. So for example, if 1 kilogram goes into the pump, then how much comes out at the top? 1 kilogram. It was wrong of me to say if 1 meter per second travels, water travels at, then it means 1 meter per second at the top. In fact, if the water at the bottom is going really fast, then the water at the top can be going really slowly if the pipe gets wider. Okay, because if the pipe gets wider, then more water can come out at a slower speed. So in fact, you can change the speed of the water at the top by changing how big the pipe is. In fact, if you made the pipe really small at the top, what would happen to the speed at the top?
So fast.
It'd be really fast.
Isn't there Pascal law?
Oh yeah, well, we'll talk about that in semester 2, but I hope, are we clear? I don't think it's called that. It doesn't matter. Are we just clear about what I'm saying about water? So, what we can say is, if we picture 1 kilogram of water here, and it travels up to the top, the most height we can make is when the water reaches the top, just about reaches the top, and it's not really moving so fast. So again, we can just say the kinetic energy down here was enough to give it all potential up here, and not really any kinetic. In other words, KE equals PE. Okay, are we okay with that? Yeah. So I'll just read through this question now on page 87. Okay. So we have our So here's our water coming along here, and then here's our pump, and then here's our water coming out. So we can say the kinetic energy here equals the potential energy here. So we get a half mv squared equals mgh. Cancels. H equals v squared over 2G, which here would be 1600 over 2 times 9.81, which is 19.62, I believe. I don't know if I have my calculator, do I? I do. $81.5? Yep. Okay. Right, next. This is number A3. Okay, B part. Now, it says here that the water, the mass is 1800 kilograms per minute. So that would be divide by 60, 30, was it? 30 kilograms per second is how much mass we're getting. Yeah.
Divide by 60.
Yep. Okay, yep. Now, what is the force on the hose? So, in other words, here, if I go back to the diagram, what's happening is that there's a force here, and that's why, well, you know, it's a pump, it pushes the water up to the top. So there's a force there. And how can we get the force? Hey, why are you late? Didn't you just have chemistry? This is ridiculous. No, come back for the second class. What was I saying? Oh yes, there's a force. Now you have this formula for force from Newton's second law. The change in momentum over the change in time. And what's the formula for momentum? Mass by velocity. So it's just the mass by the velocity divided by the time. So that would be 30 by 40 over 1. So that's 1200 newtons.
But is that the formula for momentum? Change in momentum. That's part of the momentum.
Sorry, yeah, it is the change in momentum. Or if you want to think about it the other way, is it's the small momentum that's... Yeah, I know what you're saying, that it's mv minus mu. So here, that delta P is the small change of momentum for all the different masses. It's not one mass. What you're thinking of, which is fine, is when we're looking at one mass and we change its momentum. This has the other meaning when we remember doing the rockets. The delta... Yeah, the delta P is how quickly the momentum of the gas is coming out of the rocket, you know, how quickly that's changing per time. That's the up force of the rocket. It's a similar idea here. That delta P, in other words, is the small momentum that's being given to each delta M, each small mass. Maybe that I can see why that's confusing. Maybe it's better if I just wrote P over T. But anyways, that's the answer, 1200. Yeah. I didn't finish B?
Yeah, the question is what's the momentum given to the water?
Okay, sorry, I just got what was the mass per second. Yeah, so, well, momentum is mass by velocity, so I just multiply this by 40, and I have 1200 there. Okay. So here...
Is 40 the speed?
It is, isn't it? So just multiply this by 40 and I get 1200 kilogram meters per second.
So what is the delta T in the C?
Huh?
That change in time?
Delta T is like the change in time, or in this context is the unit of time, the rate that the change is happening. It's like the increments.
Rate of change in momentum.
Yeah. It's all per second, so the delta t's are seconds. Right, now, I said yesterday that power is force by velocity, which is true. However, if we're being really honest, it's not force by velocity, but rather average force by average velocity. Okay? So true, power is force by velocity. But that formula works well when force is constant and the velocity is constant. Okay? Now tell me this. In this example, is the force constant? Well, probably. The pump is giving it a constant force. Is the velocity constant? No. So what we could do is use the average velocity here instead. Now what's the velocity at the beginning of the water? 40. And what's the velocity at the end for the water?
30.
No. No. Because we're assuming the water just about reaches the top.
0.
So it's 0. So what's the average of 40 and 0? 20. Right? So if I was to use this formula, I should use 20, not 40. Because the velocity needs to be constant, and if it's not constant, then you should use the average. This is the problem I had yesterday as well when I was doing it quickly at the end. I put V as 40, whereas I should really put in 20. Now that's not the only way to do it, so I'm going to do it two ways. You choose whichever way you prefer. So the first way is power equals force by average velocity, if your velocity is changing. And of course, if your force is changing as well, you know, but we won't complicate that right now. So in this case, it would be 1200 by 40 plus 0 over 2, which is, what is it? 24 kilowatts, yes? Now I said there's a second way to do it. I'll just call this method 1. Okay, the second way to think about it is thinking about what's happening. So what's happening here is the water is taken from the ground higher up. So what happens to the water? It gains potential energy, doesn't it? And how does it gain it? Who's given it the potential energy? The pump. So what work or what job is the pump doing? It's lifting it, isn't it? It's, in other words, it's giving something potential energy. That's its job. The work it's doing is raising stuff. In other words, the work it's doing is giving things potential energy. The work is to give potential energy. Now, let me just check something here. What was the height here, by the way, guys? I don't have it. 81.9. 81.5. And what is the mass here? 30 per second, is it? Yes? Okay. Yeah. Yeah, actually, MGH. I just put in the numbers here and you get the same thing, 24 kilowatts. That's the work done. Oh, sorry, yeah, you're right, sorry. That's, to be clear, yes, you're right, that's joules. So then how do you get power? Power is work over time, so it'll be 24 kilojoules over 1 second, so then that is 24 kilowatts then, yes. Sorry, so work is to give potential energy per second. Let me just make that clear. So it's MGH. That is the... No, that's wrong. Work is give potential energy. Power is give potential energy per second. Yeah. So you have two ways to get to the answer there. And which way do you prefer? The second one? I have a feeling that that's what they probably wanted you to do, because what was the first thing they asked you to calculate in the question? Height. But you can see you still get the same answer if you use the other formula. Is okay? Yeah? Sorry, so I didn't mean to rush that at the end of the last class, but now you have a nice, clear answer here. Okay, so let me pause that, and then the next one